Good evening, class. So tonight we'll be doing a Laplace transform, and let's start with a summary first. Okay. So this Laplace transform. Now we are talking about a Laplace transform of a function ft. So the function is a function of t. All right. And then after Laplace transform, we actually change the variable, and it becomes a function of s. Okay. So after Laplace transform, the variable is changed from t to s. So let's see the definition of Laplace transform. Now this is actually the definition. All right. So fs. Now how to compute this Laplace transform of ft is actually you take the ft and then you integrate. Okay. You integrate respect to t. And you need to multiply this e to the power minus st and integrate. Okay, and we notice that the range of integration is 0 to infinity. All right, so this is how we get Laplace transform from the first principle. Okay, so usually we talk about say you want to get it from the first principle, right? So meaning from this definition. Okay, this one is actually a definition. Maybe I put in here. So this is the definition of Laplace transform. Okay, right. Yeah. Okay, so now the next thing we do is that we treat this Laplace transform like an operation. So if you treat it like an operation, so let's denote it by the letter L. So you notice that this L is slanted, a bit slanted like that, right? So we call this a script L, right? So it represents the Laplace transform operation. So when you put LFT, so the meaning of this is you take the Laplace transform of ft, all right? And we already know that the outcome is capital Fs. So the variable is changed from t to s, okay, right? So now this equation here, Laplace transform of ft is fs, right? So what we do next is we can apply inverse Laplace transform to both sides. Yeah, both sides you go and do inverse Laplace transform. Okay, then what will that give us? Now it will give us this. Now if you inverse Laplace transform the right side, then it will give me this, right? And then if you inverse Laplace transform the left side, now you inverse Laplace transform, then here Laplace transform, right? So that means they will be like neutralized already. So that's why that will give you this ft. Is it okay? All right. So what we have here, these are actually two very important relations between the small ft and the big fs. All right. So it relates the small ft and the capital Fs. So what's the relation? Well, the relation is like this. Laplace transform of ft is capital Fs. All right. And if you inverse Laplace transform capital Fs, that will give you back ft. Okay, no? So this is the relationship between the small f and the big F. Okay, and we have to always remember this. Okay, right. So then the next thing is, let's go to two very famous properties of Laplace transform. These are like the well, it's a property of Laplace transform. Okay, right. So first we look at this time shift. Now this time shift, this formula is called time shift formula. So this time shift formula is like that. Okay, so you see we got Laplace transform of this gives you this. Now let's look at the things inside. So we got the f argument is a t minus t naught. T naught is a constant. And then u t minus t naught. All right. Now this u here, do you all know what is u? Class, do you all know what is u or not? Any idea? Yeah.
So the step function?
Yeah, it's the step function. All right, it's a unit step function. So this is the u here. I think you all, after doing Laplace transform, well, must become very familiar with this. Okay, so if you Laplace transform this thing, then this is the outcome. All right, and then of course you see that here there's a T naught, right? Obviously it's the same constant T naught. And then you see here capital Fs, right? Times capital Fs. And then you know, okay, here got a small f, right? Here got a big F, right? How are they related? Well, related by this. Okay. Then the next formula is a frequency shift. Well, frequency shift is like that. You Laplace transform this thing. All right, here got a S naught. S naught is a constant. And the outcome is F. And then the argument is S plus S naught. And of course, this S naught and this S naught are the same. All right, yeah. So, well, tonight we'll use this formula quite often. Okay, then the next thing I want to show you is our exam appendix. Yeah, see, this one is our exam appendix, right? So what you are looking at now is actually the Laplace transform table, right? So you look at this table. Now in this table, can you see here? This is the FT. Let me circle here. You'll see here, this one is the FT, right? And then over this side, this column is the capital Fs. Then of course, you all know the meaning of these two, right? Laplace transform of the Ft here is the capital Fs here. All right. And then you see they list down some common functions, and then they will list the Laplace transform of the function. Okay. Now, for example, this one, then you see ut, Laplace transform is 1 over s. All right. So you see, there are, these functions actually quite useful, right? Okay, see, right? Yeah. You see, even things like, t e to the power minus at, this one you also know the Laplace transform. Okay. Now, sine omega t, cosine omega t, of course you know. And then you will see these two. You see these two or not? So number 9 is called damn sine, and number 10 called damn cosine, right? So you see, it's actually quite complicated. You see, the function is like that. So this one, the Laplace transform of this is also given. All right, yeah. Then of course you've got other things like what linearity, differentiation. See, quite a lot, right? So there's a second page. So if we go to the second page, so this is the second page, right? Now, actually, our time shift is also here. Can you see? This is our time shift formula, right? This is our time shift formula. You Laplace transform this one, you get this one. Now, even just now, our frequency shift, see, it's also here. All right. Yeah. So this table is very useful. So I will advise you that every night before you go to sleep, you go and read this table. All right, so that you are familiar with what is given. All right, ask you to read. It's not ask you to memorize. Okay, so if you read it every night, then I'm sure you will become familiar with it. Then you sure will know, if you say sine omega t, then you will know that, this sine omega t, you have the Laplace transform here. Then sine, you also know there's a formula here. Okay, yeah. So just to be familiar with what is available. Okay, so I think we can now go to our question. So this is our first question. So here we want to compute the Laplace transform based on the definition of the Laplace transform. Okay, so we got all this here, and then you want to find the Laplace transform. Oh yeah, I forgot to tell you one thing. Now you see all this function of t, they all got the ut behind, right? Actually, I forgot to tell you that in our Laplace table, now you see your ft here, you notice that the ft that they put here, other than number 2 and number 3, and number 4, right? Other than 2, 3, 4, behind all these 5, 6, 7, 8, 9, 10, you see that behind they don't have the ut, right? But actually it is there. All right, just that they didn't put down. So you see all this e to the power minus at, actually behind there's a ut. Okay or not? So the meaning of ut actually is just to tell you that the t here can only be greater or equal to 0. All right, so that's the meaning of UT. Okay, not right. So let's go and do by definition. Now let's go and check the definition. So that's on our first page, right? So this one is our definition. We draw a line here. No need to draw a line. So I already written here, right? So this is the definition. Okay, so let's go and look at our solution. Okay, so the first question is e to the power minus 2t ut. All right, so you realize that according to our definition here, I should take e to the power minus 2t, and then there's a ut. So actually here there's a ut, right? Actually here there's a ut. Okay, but how come you don't see it there? I'll explain in a moment. So actually there's a e to the power minus 2t and then ut. So this is your ft, right? Then you multiply e to the power minus this thing. Then you go and integrate, correct? Okay, now I explain why. Actually there should be a ut here, right? But here why you don't see it? Actually, why you don't see it here? Any idea why this ut you all don't see it there? Why is it invisible?
Is it because you're including the range of integration?
It is because what in the range of integration?
I mean, yeah, you're starting from 0 to infinity, right? I mean, that should be the same.
Yeah, correct. Your range of t is from 0 to infinity. So when your t is between 0 to infinity, what is the value of ut there? If your t is greater or equal to 0, 0 to infinity means it's greater or equal to 0, right? So what is ut? What is the value?
So it's 1.
Yeah, it is 1. So actually it's because the ut is 1 here. So that's why you don't see it. So actually it's 1, right? Okay, so now let's go and do this integration. This one you all know how to integrate, right? I just combine. Then after that, integrate respect to t, and also put in the limits. Then you get to here. Okay, right. So then the next one, okay, sine 3t ut. Now here also got a ut, right? So I think you all know already, this ut, in the range of integration 0 to t, this will be 1, right? So that's why your Laplace transform of sine 3t, actually the ut value here is 1. That's why you don't see it. Okay. Okay, so now we need to handle this integration, right? So sine t times e to the power this thing, right? So actually this kind of integration, how would you do it? How would you do this integration? Have you all done it or not? Yeah, class?
Yep.
This thing will move by its own one. Okay, class, do you all know how to do this one? Any idea how you do this?
You separate them. Yeah. No. It's a. You look at the table.
Oh, look at the table. Oh, you mean the table that I showed you all last week, is it?
No, you just show us just now. The Laplace.
Just now. Oh, you mean this one?
Yeah.
This?
Yeah, that's inside of that.
How come I never move and then this thing will change page by its own? That is very funny. Okay, so here, this one, you mean go and look at this? You mean go and look at number 7?
Yeah.
No. This question you cannot say look at number 7, okay? Because they ask you to find it based on the definition. So that means ask you to do this. Okay, so you cannot look at the table. Yeah. So how would you integrate this?
You do it by part.
Integration by parts. Actually, you want to integration by parts also can. But then, because this one sine 3t, actually we know this, I think you all call it Euler formula, right? Is it correct that you all call it Euler formula? This is a sine 3t. We also have a similar one for cosine 3t, all right? So you can write it as e to the power of 3it minus e to the power of minus 3it divided by 2I. Okay, I and j are the same. Okay, yep. So this is the one. So if you use this, because you got e to the power something, right? So then you can combine with e to the power minus st, and that will help you a lot in the integration. So you will make the integration a lot simpler. Okay, then you just do like that. Then you can get the answer. Okay, right. Now let me go to part C. Okay, part C is a TUT. So, well, you also know the UT here from 0 to infinity is 1, right? Yeah, so that's why you just have like that. Okay, this one, how do you integrate that? Any idea? What method do you use?
You do it by part.
Yeah, this one is integration by parts. All right. So we all know integration by parts, right? So what we do is we let u be t. So we let u be t, and then the rest will be dv. All right. So that's why you see this. Okay. So then you just go and do that, and just go and do integration by parts. All right. So I won't go through all this. All right. So this integration by parts. Okay, let's go to part D.
Professor, what do they mean exactly by based on definition of Laplace transform?
Definition.
Yeah.
Yeah, this one. Can you see here this formula? You know, fs equal to this thing. This is the definition.
So basically, they ask us to integrate it out.
Yeah, you got to take your ft, multiply e to the power minus st, and integrate from 0 to infinity respect to t.
Oh, all right.
Yeah, so this is called definition. Yeah, this formula is called the definition. Okay. All right. So maybe we go to part D. Okay, part D. Now, part D is a little bit different. You realize that this is a t minus 2 times ut minus 2. You see, all this is ut, right? But this one is ut minus 2. So what is the value when t is from 0 to infinity? Okay. So what is the value? So here, let's go and see this thing. If you go and integrate, you know, t from 0 to infinity, wait, first of all, we look at this. So your ut minus 2, t minus 2, okay, it will be equal to, now, same thing here. All the unit step function, it can only take two values. It's a 1 or 0. Okay, either 1 or 0. So depending on the argument inside. So if the argument inside is greater or equal to 0, then it will be 1. If the argument inside is less than 0, then the function value will be 0. Okay. So in this case, when will ut minus 2 be 1? For what range of t? For what range of t? What is the range of t here? Yeah, class, any idea?
Like 2.
Actually, it's for t minus 2 greater or equal to 0. All right, is it okay? I'm not sure whether you okay or not. And when it is 0, over here, your t minus 2 is less than 0. All right, now why we have this? Because this is what we know. All right, ut, as I say, only take two values, 1 or 0, right? Is 1 if t greater or equal to 0, the argument, okay, right? And it is 0 if your t is below 0. Okay, so this one we should know. Yeah, this is the meaning of UT, unit step function. All right, so based on this, the argument must be greater or equal to 0, then it's 1, right? Okay, so now our argument here is t minus 2. So for this to be 1, that means your t minus 2, the argument, must be greater or equal to 0. And in other words, that means t greater or equal to 2, right? So in other words, this is actually t greater or equal to, all right, equivalent to this. And then it will be 0 if your argument, which is t minus 2, is less than 0. And of course, if we shift it, then we know that this is just t less than 2. Is that okay? All right, class, is this okay to you all? All right, now, any questions? Okay, so if you have no question here, then you know already your ut minus 2 will only be 1 for t greater or equal to 2. All right. Okay, so now if you look back, like just look at your part C. You know that later on you want to integrate t and then from 0 to infinity, right? 0 to infinity. So you just imagine, if you integrate 0 to infinity, let me change the color to a darker one. So if you integrate 0 to infinity respect to t, all right, and then you know that, this one will only be 1 for t greater than 2, and you will be 0 for t less than 2, all right? So therefore, your integration, 0 to infinity, actually you can split into 0 to 2, and then plus 2 to infinity, right? You all know this, right? You can do this to 2 to infinity, all right? So over this part, 0 to 2, right? Your t is from 0 to 2. Now, what's the meaning? Now, 0 to 2, that means your ut minus 2 is what? T less than 2, right? So it's 0. So here, your integrand will be 0. Okay, because 0 times anything also 0, right? So as long as you have this term 0, then you know that your whole integrand will become 0. So you are integrating 0. So you won't get anything here. And you only will get this part to infinity. And over here, your ut minus 2 is 1. Is it okay? All right. So it is because of this. That's why you see that when you want to Laplace transform this, so by right, we should integrate 0 to infinity, right? But you realize that I put here, I integrate 2 to infinity. All right, and then I got the t minus 2, and the ut minus 2 here is 1. So there's actually a 1 here, okay? Then e to the power minus st dt. Well, any questions, class, about this? Why I integrate from 2 to infinity? Any questions? Okay, right. So if this is clear, then we will just carry on from here, right? Okay, then how do we integrate? Now here, t minus 2 times this, right? So, well, one way you can do is that you want to multiply out also can. T times e to the power minus st, and then minus 2 times e to the power minus st. And then I think the first integral, you need to do integration by parts. All right, so then you know how to continue, right? Another way is what I'm going to show you here. Now here, actually, we go and change the variable. Okay, so the t minus 2, I call something else. And by doing so, I actually need to change the limits of integration as well. Okay, yeah. So I need to change everything to tau. This thing is called tau. Okay, yeah. Then it becomes like that. Okay, then you see 0 to infinity, right? So when you come to here, to carry on further from here, actually also need to do integration by parts. All right, so still need to do integration by parts, right? Then you can just do it like that. Okay, but there's no need for you to change the variable. Here actually no need to change the variable also can. Here if you just go and multiply out, Then you can integration by parts here for the first term. Then second term, you can evaluate. Then you no need to go through all this. Well, because you go through all this, you also need to do integration by parts. Okay, all right. Is it okay, class? Okay, so now we go to the next question. Okay, let's go to the next question. Okay, here is the next question. So here we want to sketch the function given by this. All right, so this is a 1t from 0 to 2, 2t from 2 to 3, and 0 elsewhere. So I think this one sketch no problem. And then after that, we want to write gt in terms of delayed step function. Delayed step functions. Okay, now step functions, you know, ut is called step function. Just now we have a ut, right? Ut is called step function. What about delayed step function then? What is this delayed? Delayed means that it's something like this. Ut, not just t, but t minus a constant. Okay, so the argument is t minus a constant. Somewhat like our earlier question like that. And you see here got ut minus 2, right? So this ut minus 2 is called delayed step function. Is it okay? So here they ask us to write gt in terms of delayed step functions. And after that, then you want to find Laplace transform of gt. Okay. Okay, so let's go and do this one here. Well, first we want to go and sketch this one, right? Yeah, I think the sketch is not a problem. Do we have the sketch here? Let me see. Oh yeah, so this one is actually the sketch. So you see it is 1 from 0 to 2, okay, then 2 to 3, then the value is 2. And then here it is 0 elsewhere. Yeah, so it's 0 elsewhere. So this is the graph. Is it okay? All right, all. So now,
so Professor, like, can we draw on the vertical line as well?
No, you cannot. Why you want to draw vertical lines?
What? Yeah, I mean, I'm just curious. Yeah.
No. You don't draw vertical lines. All right, because the function is 1, so it's just 1, right? So why you want to draw the vertical lines, right?
Yeah, but in the step function, like you just normal ut, like so there's a vertical line between 1 and 0, right? Over there.
No, actually it's not vertical line. Actually it's a dotted line like that. Okay, just to indicate that this point is when t equal to 2. Actually it's not solid line. Okay, yeah. So actually the function is like that, and then this is the value 2, and then this one is a value 0. Here also value 0. All right, so it's like that. Okay. Yeah. So we want to write it in terms of delayed step function, right? Yeah. And then yeah, my graph is actually here. So I hope you all can remember this graph. Maybe should we draw it here? Maybe we should draw it here, huh? Let me change color. Okay. Let me change the color here. Color. Let's do gray. Okay. So it is like that. All right. And then we got a 2 here. And then there's a 3 here. All right. So let me change color again. So we have a pink one. So we know that this is 1. This is 1. And then we have a 2. All right. And then this one is actually 0. Okay. Yep. So it's like that. No? So maybe let's draw in some dotted lines. It's gray, right? Yep. So this is 1 and this is 2. So let me put in some dotted line. All right. So actually it's the pink one that is the graph of the function. Is it okay? All right, well, now looks quite nice, huh? Okay, so now let's go and do. Okay, so now let's go and get this delayed step function, right? So let me do here. Okay, so first of all, let's look at the graph of UT. Everybody see this? This one is a graph of UT, right? Yeah. So we see that it's actually 0 for t less than 0, and it's the value is 1 for t greater or equal to 0. All right, so this is the graph. Yep. And well, the graph is actually highlighted, right? So how should we, well, I mean, we look at this graph. You already see that this part here, well, you actually get this part, right? And this is 1, right? So you actually get here 1. Just that this one is continue forever, right? Which you don't want. You want it to go up to 2 for t greater or equal to 2, right? Okay. So then what we do is that well, remember just now our ut minus 2, right? So if we go and take a ut minus 2, well, this is the graph of ut minus 2. Okay. Now ut minus 2. Actually, just now we just have it, right? There you see, I put down my definition here. Your ut minus 2 is 1 for t greater or equal to 2. So that's why you see, for t greater or equal to 2, the value is 1. All right, and then t less than 2, the value is 0. So this is how it looks like. Okay, this is ut minus 2. Right. So now, if you want to get, this part, you get 1, right? And then this part, you want to jump up to 2, right? So then you, by looking at these two graphs, okay, if you add them, you go and imagine if you add them, what will happen there? You add them. Then you realize that, from below 0, of course, it's still 0 lah, because here also 0, right? From 0 to 2, this part is 0. But from 0 to 2, this part is 1, right? So 1 plus 0 will give me 1. All right. So that means that if I add together from 0 to 2, I still get 1. Okay. But after 2, now this one after 2 is 1. This one after 2 also 1. So then it becomes 2. Okay. So therefore the graph is like that. Any questions, class? Is it okay? I hope you can see that. Now this one, we find that, okay, now we actually get this part here. This part already got it, right? 0 to 2, you get 1, right? After 2, you also get 2, right? But here after 2, it's not forever 2. When it is from t onwards, t equal to 3 onwards, you want to bring it back to 0. All right, so how do you bring it back to 0? So it looks like you need to minus 2, right? Yeah, minus 2, then becomes 0. And then this minus 2 is only for t from 3 onwards. Yeah, it's only from 3 onwards, then you minus 2. Okay, so how do you capture this effect? Only for t from 3 onwards. From 3 onwards. All right, so therefore you think, wow, maybe I need to look at ut minus 3 lah. And you can imagine, right? This one ut minus 2, then this number here is 2, right? This is ut minus 3, then this number here will be 3, right? So then you know, I need to look at ut minus 3. But ut minus 3, you see the function value here will be 1, right? But now you want minus that, and you want minus 2, so that doesn't mean. So that means, wow, maybe you need to look at minus 2 times ut minus 3 lah. So this is actually the graph. Okay, so you see below 3, 0. More than 3, actually your ut minus 3 is 1 lah. 1 times minus 2 is minus 2, right? So that's why you get this. All right, so that means from 3 onwards, you get minus 2. Okay, so now, what about now you add this one and this one? Now you add. What happened? And you realize, from 3 onwards, then this one 2, this one minus 2, then becomes 0, right? What about before 3? Before 3, what will happen? Now, before 3, this one is 0. Before 3 is 0, this one 0. So 0 add anything, it will preserve this one, right? It won't change before 3. Right? So the things before 3 will still be the same. So you still get like that. It's only after 3, then you get 2 minus 2, then you get 0. Okay? So now you get like that. Then of course you look at this, you look at our this graph here, right? So now you see already, so they are the same. So any questions, class? No problem, right? Okay. So if no problem, then that is our I mean, this is how we can do. I wonder whether you all do by this method. Any one of you did this method there? Yeah, class, any one of you did this method? Like what I do?
I did this method.
Oh, you did this method. Okay.
But
Right.
actually in exam, do we need to show all this or we just present the answer if you can see?
Well, if you can see, then you can just present the answer.
Okay.
I mean, I draw so many steps is to show you the step by step. Okay, let me show you another method. So that's just now that one is like method 1. So it's like through observation. All right. So the other method there is not really observation. It's actually a more general method. Okay. So let's see what is this general method. Okay, so first of all, we look at the graph of ut minus t1. T1 is a constant. So then we know, okay, after t1, the value is 1. Before t1, the value is 0. Okay, so this is this. Now I want to draw a similar one. I want to draw ut minus t2. And of course, t2 is a different number from t1. Okay, so let me go and draw this. Now, of course, the graph will look similar. Now, suppose your T2 is here. It's actually more than T1. All right, then this will be the graph. Okay, all right, all. And then you can see the third line. I want to take the first one minus the second one. Okay, so if I take first one minus second one, can you all see how it is going to be like? Can you see how it's going to be like? Yeah, you got T1 here, you got T2 here, right? Below T1, what is the value of this function? Anyone? Below T1, what is the value of this? Yeah, class, are you all following me? Can you all hear me or not? Below T1, what is this one minus this one? Do you understand what I'm asking?
Not really.
Do you see this ut minus t1 minus ut minus t2? You see this, right? Now I want to get the graph of this. Okay, I want to get the graph of this function. So what do? You take this graph, go and minus this graph. Okay, so now I'm asking you, below T1, that means from minus infinity until T1, what will you get there?
0.
Yeah, you will get 0 minus 0, which is 0. Okay, then from T1 to T2, what will you get?
1.
Okay, 1 minus 0. And then from T2 onwards, imagine T2 onwards.
0.
Yep. So this is what I'm asking. Okay. So actually, if you go and draw all this, this is what you have. All right. So you realize that this ut minus t1 minus ut minus t2, it gives you a graph like that. It's only 1 between t1 and t2. So it's like single out the interval t1, t2. Only in this interval, the value is 1. And then outside this interval, is 0. Okay, so this is actually very powerful. So that means whenever you want to single out the interval, right, the value is 1, you do this. All right, because you see outside 0. It's only between T1 and T2 you get 1. Okay, right. So how to use this? Now you can see that I'm giving you an example here. Now look at this example. I think this example is even more general than our question here, right? So here, say you got T1, T2, T3. All right, below T1, more than T3 is 0. T1 to T2, say you got a curve. I don't know what curve it is. So suppose we call it GT. Then T2 to T3 is another curve. So suppose this curve is called HT. All right, and the whole thing, the whole function is called FT. Can we write down FT in terms of delayed step function? Actually can. All right, so you notice that this one is general G, general H, right? So how do you observe? So maybe your observation just now maybe cannot work out, but this one can work very well. Okay, because if you use this, you just single out the interval and the value is 1, and outside is all 0. All right, so let's single out T1, T2. Now, if you want to single out T1, T2, so what you do is your function, you take ut minus T1 minus ut minus T2. So that means only T1, T2, the value is 1, right? Outside all 0. And then you multiply GT. You multiply GT means that now between T1, T2, the value is GT. Outside there, outside all 0. Okay. And then because outside all 0, that's why if when you add the second part, it will not affect anything. Okay, now you add the second part here. Now you single out T2, T3. So when you do ut minus T2 minus ut minus T3. So only between T2, T3, the value is 1. Okay, but the value now is HT, right? So you times HT. So that will give you this part. And outside all 0. So when you add these two together, this is what it will give you. You all get it? Any questions? Okay, so how about we apply this to our function here? Okay, so our function is even simpler than this one, right? So let's apply to our function here. Now, if you apply this to this function, okay, since I also have the, so let's use this ut minus T1 minus ut minus T2, all right? So apply to this function. So first of all, your T1 is like 0, 0 to 2, okay? So your T1 is like 0, your T2 is like 2, okay? Now your this function value is 1, right? Yep. So this is what I'm going to get. So let me type here. So I will get GT, the function that you want, is actually 1 times, because this value is 1, right? Yep. If it's not 1, then of course you will multiply some other thing. So it's actually 1 times u t minus T1 minus ut minus T2. T1, T2 here is your 0, 2. All right, so this is your T minus 0 minus T minus 2. Okay, so that will single out this part. Okay, the rest all 0. Right, now you go and single out this part here. So the other part there is well, the function value now is 2. So 2 times, okay, so let me single out 2, 3. All right, so now your T1 is like 2, your T2 is like 3. All right, so ut minus T1 is 2, and then minus ut minus 3. All right, so this is how I get it, just by using this. Okay, so here we actually no need to go and do observation or whatever. And even functions more complicated than this, we can also do. All right, so after you write this down, you just do some simplification. So you just multiply out, do some simplification. Yeah, see, very strange, it will turn by itself. So then you will just get this. It's okay. All right, so this is the second method. And I think this method is more general. Okay, yep. Okay, so now we got this already, right? So let's go to part B. So we are going to do a Laplace transform now. Huh? Okay, so this is our GT, right? So we're going to do Laplace transform. Okay, so we just go and Laplace transform every term, right? So see Laplace transform every term, right? The first term, this one is this one. This is from your Laplace table. Is it okay? All right. Now, second term and third term. Now, obviously, your second term is this one, right? Yeah. And of course, your third term here is actually like this. So let me show you why your second term is this. Okay, why your second term is this? Actually, we are using time shift. Let me show you our formula again. Okay, so actually your second term, to get your second term here, actually we are doing the time shift. So let me explain why, how we get that. So the explanation is actually here. So it's on a separate page. So this is actually our time shift formula. Well, exactly the same as what I have here. Okay, our problem is we want to Laplace transform ut minus 2, right? So I say I just want to show you this term. Well, once we know this, then this one will be similar. Okay, right. So we want to Laplace transform ut minus 2. And we think that we should apply time shift. Okay, first of all, why we think that we should apply time shift? Well, that's because if you look at the time shift formula, there is a ut minus t naught here. Okay, can you see? There's a ut minus t naught. So whenever you see that your function, the one you want to Laplace transform, also got a ut minus a constant, then you will want to use time shift because it will match the formula. Okay, remember, when you want to apply a formula, you need to match the formula exactly. Okay, right. So then, okay, you say, oh, let me go and match to this formula. Then obviously, your ut minus 2, you just match to your ut minus t naught. And from here, you actually will know that your t naught is 2, right? Yeah, t naught actually is 2. But what about your ft minus t naught? Your this one, you say you match to this one, you say you go and match to this, right? Then what about your ft minus t naught? Your ft minus t naught got nothing. Is it nothing? Well, actually, it's not nothing. Okay. Actually, you may not realize this. How many of you realize this? That your ut minus 2 is ut minus 2 times ut minus 2. How many of you know this? That your this one is this one? Do you all know this? Well, probably now you know, right? You know that this one is equal to this times this. Do you know why it's equal to this times this? U equal to U times U. Actually, it's very obvious. It's actually very obvious, right? It's just from the definition. Your ut minus 2 is 1 for t greater or equal to 2, right? And 0 for t less than 2, right? So for t greater or equal to 2, this will be 1. This will be 1. This will be 1, right? So 1 times 1, is it 1? Yes. Then how about for t less than 2? Then this one 0. Then here also 0, here also 0, right? 0 times 0 also 0, isn't it? So therefore, this one is equal to this times this. Okay, all right, so it's obvious. Right. So now, after this, then what do you do? Since now you can write like that, right? So your ut minus t naught, just now you match to, now you can match to this one, okay? Then your ft minus t naught, your ft minus t naught, now you can match to this one. Okay, so this is this, this is this. Is it okay? All right. So if you say like that, it's okay, right? So that means your ft minus t naught here actually is ut minus 2. And of course, the t naught here is 2. Right? So your ft minus t naught actually is your ut minus 2. Okay? And then from here, we'll be able to conclude that because your ft minus 2 is ut minus 2, right? So what is your ft then? Yeah, class, any idea or not? If your ft minus 2 is ut minus 2, what can you say about ft? What can you say about ft? Yeah, class, any idea or not? If ft minus 2 is ut minus 2, then what is ft? From ft minus 2, how do we get to ft then?
UT.
Yes. ft minus 2, when you want to get ft, you just change the t minus 2 to t. Is it okay? All right, so that's how you get your ut here. So now you realize that, oh, your ft is just ut, right? Okay, I'm going to put into this formula. Now, in the formula here, there's a fs. I need to know what is fs. All right, so fs, well, the relationship between the small f, big F, right? So fs is Laplace transform of ft. Laplace transform ut, and that one from the table is 1 over s. All right, so now you got your fs already. So therefore, by your time shift, now you know your fs, right? 1 over s, right? Then over this side there, your t naught is 2, right? So that is why you get this. Is it okay? All right, so I hope this is clear to you. Yeah. Do you all like Laplace transform? Hey, class, this question is quite simple, right? Do you all like Laplace transform?
I think it's all right. Yeah.
So the rest, the rest like Laplace transform very much, is it?
Okay lah, okay lah.
Okay. Yep. I hope you all are really okay. Okay, so this is that's it. So now we know why this one is this. And of course, by the same reason, that's how we get to here. Okay, so that completes part B of second question. So this is part B of second question. Okay, right. So maybe we go to the third question now. Oh, actually, I got the diagram here. I also have it here. Okay, I forgot that I have it there. Okay, let's look at question 3. So question 3 is we want to find Laplace transform, but this time it's not from definition. So this time is from basic properties. Basic properties meaning all those things that you can find in Laplace table, time shift, frequency shift, and basic Laplace transform. All those that you can find in Laplace table. So you want to find the Laplace transform of all this. Okay, right. So that means now we are able to use Laplace transform table, and we can also use time shift, frequency shift. All right. So let me copy down the first question. So this is actually the first question. I want to Laplace transform sine t minus 2 ut minus 2. This is actually the one that we want. Okay, so this one is actually what I copy from the Laplace table. You see, Laplace table, sine t, here number 7, sine t. So the omega is 1, right? So you all know that behind actually got a ut, right? Yeah, so it's 1 over s squared plus 1. Okay, so that's why I copy here. Okay, so here, the real problem is sine t minus 2 ut minus 2, right? Well, here is your Laplace table, right? So your Laplace table is here. So you take a look at your Laplace table. So which one? Remember, if you want to use formula, you need to make sure that your function, you want to Laplace what? Whatever it is here, must be able to match the things inside exactly. Same pattern, same form. Okay, all right. So which one should we match to? Which one is too big? What shift?
Time shift.
We should do time shift. Because of what? Because of the ut minus 2. It's very obvious. Whenever you see ut minus some constant, you straight away, you go and match to time shift. And then you try to adjust the other one to make it ft minus t naught. Is it okay? All right. So here it's very straightforward. We have to match to a time shift. And our t naught here is what now? What is the number? T naught?
2.
Yeah, it's 2. Okay, so then our ft minus 2, it means our ft minus t naught lah. Then obviously will have to be the other term, right? Which is the sine t minus 2. Right, so I think it's obvious, right? I mean, I write this down explicitly so that we will be very clear. Okay or not? So now, our answer. Okay, so this is like my draft outside law. Yeah. So my answer, according to time shift, I know this is the answer. So it's e to the power of what? Minus s, and then the t naught is 2, right? So that means minus 2s, minus 2s, that, like that. So it's e to the power minus 2s, and then times fs. Okay, times fs, right? So we need to know what is fs. You cannot just write like that fs. You must write down what is fs. Okay, now what is fs then? Now actually what is fs is I see the relationship between fs and ft, right? You find that fs is what? Oh, Laplace transform of ft. Okay, so then you know that this one is you still get e to the power of this thing. So minus 2s. Right? And then you got your fs. Fs is actually Laplace transform of ft. Is that okay? All right, so this fs here actually is Laplace transform of ft. All right, so then you need to know what is your ft. And how do you know your ft there? How do you know your ft? Actually, it's from your ft minus 2. Ft minus 2 is sine t minus 2. So ft is what? What is this? Class, what is this? Ft is what?
Sine t.
Yeah, I think you got it already. Just change the t minus 2 to t. All right, so this is Laplace transform of sine t. Right? Do you know Laplace transform of sine t? And you see, it's in the Laplace table. It's like that. Okay, so that is why now your answer is like this. You get your e to the power minus 2s, and this is your Laplace transform of your sine t. So that's why it gives you this. Okay, now class, any questions? Yeah, so I think this one is all right. Let's do the second one. Okay, this is actually the second question. Okay, second question here. Now, well, you look at this. E to the power minus t minus 2, sine t minus 2, ut minus 2. So, you see a ut minus 2, right? So, what do you want to do? You want to match to which one? Yeah, have a guess. Which one you want to match to?
Time
match
shift.
Let's see.
I only hear shift. I don't know what kind of shift. Actually, it's time shift. All right, go and match the ut minus 2. Is it okay? All right, so now it's also very clear lah. So we also do a draft here. So my t naught is, what's t naught?
2.
Yeah, anyone? What is the value of t naught?
Is it 2?
It is 2. Okay, and you must answer more confidently. And then after that, so this is my ut minus t naught, right? Ut minus t naught, then match to ut minus t naught. So that means this part of your ft minus t naught will be these two terms. Is it okay? So my ft minus 2 will be this one. Okay. maybe I just go and highlight here. Highlight. So this one, this one, this is my ft minus 2. Is it okay? Yep. So this 2, this is my ft minus 2. Okay, then from here, can we write down the ft there? Because you know I will need the ft later on, right? So if this one is ft minus 2, and also you must also check, not everything you just call it ft minus 2. Is it really a function of t minus 2? When you put ft minus 2, meaning that it's in terms of t minus 2, right? Then you see, e to the power minus t minus 2, right? And sign here also t minus 2, right? So it is really a function of t minus 2. Okay, if this one is t minus 1, then you cannot say this is also called ft minus 2. Then cannot. Okay. Okay, but here it can. And from here, where's my ft there? Where's the ft here? So I think you all know the trick, right? If this one is ft minus 2, then how to write ft? What would that be? Your ft will be what? Yeah, class, anyone?
e to the power minus t sine t.
Yeah, that's right. So you just change the t minus 2 to t, right? Yeah. Then sine t. Yeah, no? Yeah. Yeah, so it's just like that. All right. So again, by our time shift formula now. So according to formula is e to the power of your t naught is also 2 here, right? So it's minus 2s. So that's this part. And then you got your fs. And then now we are more expert already. So fs I know is Laplace transform of ft. Yep. Which is your ft here. I need to Laplace transform ft. So if you look at Laplace transform this thing, then you see, then you will tell yourself, this one not easy. Also looks like it's another problem, right? It's like a problem within problem, right? Yeah, Laplace transform of this. But if you go and read Laplace table every night before you go to sleep, then you will know that this one actually is in the Laplace table. All right, and you just go to Laplace table to see. Just go to Laplace table to see, y'all. Are you able to see? Can you see something like that? E to the power of something minus t and then sine t. Do you see it? You see it? Tell me what is the number of the formula? Anyone?
9.
It's actually 9. Can you see it's then sine? It matches very well. This one is e to the power minus at sine omega t. All right, so if you are going to use this, that means your a is what? What's your a? And what's the omega?
A is 2.
Hey, this one, this one, I'm talking about this one. You want to find Laplace transform of this, right? Where this is your small f, right? So now you're looking at your damn sine, right? So your a is what? Your omega is
1.
what?
A is 1.
A is 1. Then omega, also 1. All right, and this is the Laplace transform. 1 over s plus 1 square plus 1. Okay, so if you know this, then life is simple. Life is simple, okay? Then you can just write your answer here. Then e to the power minus 2s. Oh yeah, this one I actually multiply up already. So actually it's like that. 1 over s plus 1 square plus 1. Okay, so this is by your then sine. You see? This one you go here, then straight away you get it here. Is it okay? All right, now everyone clear? Everyone clear? There's some chat here. You want to change your com. Your battery is dying. Yeah, how come you never say earlier? Now I already switch on the battery. Yeah, I already switch on the battery. Okay, I mean I switch on the power. Okay, so everybody okay, right? Yeah. Well, maybe next time you want to tell me something, you just unmute and tell me. It's easier, okay? Yeah. Okay, so actually when we present this solution that time, we never read Laplace table, so we didn't know. So we go and treat this as another problem, and then we go and do frequency shift. Okay, then we go and do frequency shift and get that. But as you can see, actually we can get this directly, all right, if you know the Laplace table. Okay, let's go to the next part. So this is the next one. This is the question, the first line, you want to Laplace transform this. All right, so we see here is e to power minus t sine t minus 2 ut minus 2. Okay, now here, when you say you want to Laplace transform, right? Which formula you want to use first?
Time shift.
Yeah, you will still use time shift. Although the e to power minus t here make you think of, maybe we can use frequency shift. All right, but we go and match the ut minus 2 first. Okay, yeah. So usually if you see a ut minus 2, you go and match the time shift first. All right, and make the other function ft minus t naught. Right? So I'm going to make the function, which is this 2 here, which is these 2 terms here, right? This one obviously is your ut minus t naught. So this one, I also want to make it to be a function of t minus 2. Is it okay? But this one, you cannot just simply call it ft minus 2, because currently it is not. All right? Because although this one is a sine t minus 2, but here this is e to power minus t. There's no t minus 2 here. Okay, so you cannot just call the whole thing function of t minus 2. You have to rewrite. All right, so let's go and rewrite. Yeah, so we say rewrite, right? So how you rewrite? This is the way you rewrite. Okay, this is actually the final result. You may wonder actually how we rewrite all. Okay, maybe I type here, then you understand. So the minus t, which is the exponential to the power minus t, right? Your minus t here, you actually want t minus 2, correct? Yeah. Your aim is to get the t minus 2. So you see, I put minus and then bracket, and then I put t minus 2, which is the thing that I want. And then I neutralize it. T minus 2 plus 2. So actually I didn't change anything, right? Yeah. But I got the t minus 2 coming out. All right, and then I just multiply it out. So this is a minus t minus 2, and then minus 2. Can you all see? All right, so actually your e to power of this thing becomes e to power of this thing. So that's why you see your minus t minus 2 is here. And then your e to power minus 2, it becomes the constant here. You see, it becomes this constant here. Can you all see or not? All right, so this is the trick that we do. Okay, so now e to power minus 2 is a constant. Now, constant is harmless. You can bring outside of Laplace transform. But now inside is very nice. Can you see now inside of this one until here, right? Until here. This is now really a function of t minus 2, right? So this is like ft minus 2, then ut minus 2, right? Then you know how to do the Laplace transform. Okay, you see, constant bring outside. Now you go and do this, right? Using time shift. Yeah, this one actually is our question just now, right? So this is our 3B. This one is 3B. Yep, so that's how you get it. So, any problem, class? Any questions? Yeah, so I hope it's okay. All right, so let's do part D. Now, part D. Well, actually, the question is cosine square TUT. All right, now if you look at cosine square TUT, and you are thinking that, how about time shift, how about frequency shift? The thing is, the formula don't match. Cosine square T, do you see UT minus 2 or not? Or UT minus T not? Don't have. This one cosine square T, do you see e to the power something T and then FT? You also don't see it, right? So that means the formula cannot fit. So cannot fit means cannot use. Then what's the next thing to do? Okay, cosine square T. So you think, wow, maybe in the table, is it? Is it in the table? Then go and see, is it in the table there? Well, actually, I can tell you that it's not in the table. And then you see what are the things inside the table. Anything similar or not? This one cosine square T, right? Anything got cosine one or sine one or not? And you find that, only this one. You only have cosine, cosine, then you've got cosine omega T, right? Well, what cosine omega T is not cosine square. So that means here you've got to think, it's something related to cosine square T. You find that, you actually know this formula. Okay, 1 plus cosine 2T over 2. And then now you've got this cosine 2T, right? You see, you've got this cosine 2T, right? And this cosine 2T, actually, you know the Laplace transform. All right, so that's why if you use this formula, then it will be good because cosine 2T is actually, you know the Laplace transform. Is okay? All right. So this one you need to make use of trigo formula. Okay, so if you know this, then we just substitute this into your cosine square. So become like this, right? Then after that, you just the half you can bring out. And then go and Laplace transform each of this. The first term, Laplace transform UT, naturally is here, right? You can see very well. Then Laplace transform UT is 1 over S. Then Laplace transform cosine 2T UT, the second term. Then you use your number 8, right? So you see, straight away you can get. Okay, see, straight away you get this. Yep. Yeah, so that's the answer. Any problem, class? Any questions?
Prof, can you show 3C again? The working for 3C. Okay, thank you, ma'am.
Okay.
Okay, thank you.
All right. So you all take screenshot also very fast. Okay, then let's go and do the next question. Okay, next question. Now is something different. What's the difference there? Well, so far you find Laplace transform. Now is the other way around. This one is inverse Laplace transform. Okay. So and if you take a look at the ABC, these are rational function. These are called rational function. ABC, the form of ABC, rational function. Now, rational function meaning what then? It means it's like a fraction. All right, and then the numerator and the denominator, they are all polynomials. Okay. Yep. So these are called rational function. Part D is not rational function. Why? Because although it is like a fraction, but the numerator is not a polynomial. You got e to the power something, right? So this one is not rational function. But A, B, C are rational function. Okay, and you want to find inverse Laplace transform. So let me go back to our summary. Now, so far, we only touch on Laplace transform, right? So it's like going in one direction only. Laplace transform of this is this. Now, what about inverse Laplace transform? So actually, it's also the same formula, just that you look at it differently. Laplace transform of this is this. Let's go and inverse Laplace transform. Then you will get this. So inverse Laplace transform this thing now become this one inside. Is it okay? So similarly, when your frequency shift, Laplace transform of this is this. So that means if you inverse Laplace transform, then you will get the thing inside that. Okay, so this is what you have. Okay, so this is inverse Laplace transform version of a time shift and frequency shift. Okay, coming back to our question. So as I mentioned, ABC, these are all rational functions. All right. Now for rational functions, you want to do inverse Laplace transform. Actually, we have plan A, plan B, in our lecture notes. I don't know whether you all know or not, got plan A, plan B. You all know what is plan A? Can you tell me what is plan A?
Completing the square.
And completing the square actually is called plan B. And plan A is what?
Partial fraction.
Yeah, it is. It's partial fraction. Prof still call it plan A, plan B or not? Did Prof still also call it plan A, plan B?
Not sure.
I think he didn't. So you all figure it out yourself, right? Okay, so let's talk about partial fraction. Wait, let me talk about partial fraction. Go to my notes. Okay, partial fraction. Okay, partial fraction. Now this is the condition that you need to have before you do partial fraction. Okay, so we say to perform partial fraction, your rational function PS over QS. Now, of course, your P, Q, these are polynomials of S. So your rational function, first of all, it must be a proper fraction. Okay, what's the meaning of proper fraction? That means degree of numerator less than degree of denominator. That's the meaning. All right, so first it has to be a proper fraction. Then the next thing there, now to do partial fraction, basically partial fraction is from one fraction, then it becomes a few fractions, right? So to do that, you must be able to factorize the denominator. Okay, because if you cannot factorize denominator, then maybe you cannot become a few fractions, right? So you must be able to factorize the denominator. Is that okay? All right, so these two conditions before you do partial fraction. The first one is the fraction must be, I think I cannot draw here. Or can. A proper fraction. Okay, so degree of numerator less than degree of denominator. And the next one there is you must be able to factorize the denominator. Right? Is that okay? Okay, so let's go to our tutorial question. This one, let's look at part A. Part A, is it the proper fraction? Numerator degree, is it less than the denominator's degree? What is the numerator's degree?
1.
Denominator? Denominator?
2.
Yeah. So numerator 1, denominator 2. Okay, so proper fraction. Denominator can factorize or not? Denominator can factorize?
No.
Can what? Then they factorize for you already. S times S plus 4 already factorized, right? So they already factorized for you. Okay, so very nice. So let's go and do partial fraction. All right, so if you look at our answer here, this is how you do partial fraction. So this becomes, so this is our rational function, becomes A over S plus B over S plus 4. Is it okay? All right, all. Okay, so now we just go and get the constants A and B. All right, so I believe you all know how to get the constants A and B, right? I think partial fraction you learn in in secondary school. Yeah. So you just go and learn, you learn in secondary school, and depending on the way you learn it, some of you maybe learn it by this way, you go and equate coefficient. This way I don't like, because I don't learn this way. Okay, so that's why I don't do this. Another way there is that you go and have a common denominator, and then and then you go and substitute some value of s. That method I like better. Okay. So anyway, whatever method you use, you go and get the constants a and b. All right. Okay, so do you all use this method, equate coefficient, or you use the one I mentioned, you go and substitute the s as some values? Well, what do you all think? I mean, what?
Substitution.
Oh, you all learn by substitution one. Okay, so you just stick with the method that you learn. Okay, so anyway, we get the a and b. Then you put your ab inside. So you inverse Laplace transform this. Now become inverse Laplace transform this. All right, so actually, no matter what your constants a and b are, you look at your form. Constant over s plus 4. Now, this kind of expressions, they are very easy to inverse Laplace, very easy to inverse Laplace transform, because they are all inside the table. Hey, you see? I can see already. 1 over s, is it? That's our unit step function, no? 1 over s plus a. 1 over s plus a is here. That's what we call exponential, right? Then 1 over s plus a, you inverse Laplace transform, you get this one. Okay, so you just go and inverse Laplace transform. Inverse Laplace transform. And remember, after you inverse Laplace transform, you actually need to put in a ut. So this one ut, of course, you put another ut. U times u is still u, right? Then here, your e to the power minus at, actually behind got a ut. Can you see? Put in your ut here. Can you see or not? Then you actually put in your ut. So don't forget to put in your ut. Any questions? This one I think no questions. This one is very simple. Okay, so another one, that's part B. This is the one that you want to inverse Laplace transform. All right. So this one is a proper fraction. All right. That's very clear. Numerator degree is less than the denominator's degree, right? And also denominator can be factorized. Yeah, so then we just go and use partial fraction. That's our plan A. All right, so well, what you are looking at, why you think this one 2, 2, 2, 2, you think is it a law or not? Then everything all 2. No, it's not. So actually this one, we get this is after calculations. It's not that this one 2 means the rest also 2. So actually it's a over s plus b over s plus 1 plus c over s plus 1 squared. All right, this one is a repeat factor, so it has to be like that. Okay, so this is the final result of a partial fraction. Okay, so then you want to inverse Laplace transform, right? Then just go and inverse Laplace transform each of the terms. Okay, now do we have this there? Are these inside our table? Then we go and see. 1 over s, is it inside? 1 over s inside or not? Is 1 over s inside the Laplace table?
Yes.
Yeah, this one now you're so clear already, right? 1 over s plus 1, is it inside?
Yeah.
Yeah, that's number 5, right? Yeah, that's called exponential. 1 over s plus 1 square,
Also inside.
Yeah, if you can, if you go and read Laplace table every night, before you go to sleep, then you see, oh, that's number 6, 1 over s plus a squared. So you know it's this one, right? Then life becomes really simple. So then you will just get the result. And actually your result is downstairs. This is your result downstairs, okay? Well, wonder what is hidden here. Actually here, well, as I told you, we never read Laplace table one, okay? Yeah, so when we go to bed, we never read Laplace table. So we know the first 2, but we don't know the last. Okay, so because we don't know the last, so that gives us a lot of problem. So we actually treat this third term like another problem. And over here, we actually go and apply frequency shift. All right, so eventually we get this, which we no need if you know that this is just number 6. Okay, yeah. So I think I show y'all at least 2 instances when we don't know about Laplace table, and then we need to spend more effort to go and find out, the Laplace transform or inverse Laplace transform. Okay, so I think so that will make you read Laplace table every night, right? Before you go to bed. I'm sure that if you read Laplace table every night, you will sure get a very good sleep, right? Yeah. Okay, now let's go to question C. Now, question C is also a rational function. 2s plus 3 over s squared minus 2s plus 5 is a rational function. All right, then of course we also go and wonder, should we go and do, sorry, here. Should we go and do, yeah, should we go and do, sorry, I think I clicked the wrong file. Should we go and do partial fraction? Should we go and do partial fraction here? So this one actually, it is a proper fraction. All right, this fraction actually is proper fraction. Then we look at point number 2. If you want to Laplace transform, if you want to do partial fraction, right? So basically, you want to, from one fraction, you want to become like more than one fraction, right? So can we factorize the denominator? So that's the question. So this one, they didn't factorize for me, right? So it's s squared minus 2s plus 5. So now the question is, can we factorize the denominator? If we can, then we can go and do partial fraction. Can we factorize denominator? Anyone?
Cannot.
I didn't even finish the first lab. I have 4 things
Okay,
on my
yeah, cannot. How do you know cannot?
Press calculator.
Oh, yeah. You go and press calculator, then it gives you complex roots, right? Yeah. Yeah, correct. So that's why you know that this one cannot be factorized. Okay. Actually, last time our calculator cannot do that. So last time we actually looked at b squared minus 4ac. Do you know what is b squared minus 4ac? Hey, class, have you heard of b squared minus 4ac?
Yes.
Okay, so this s squared minus 2s plus 5, the a is 1, the b is minus 2, the c is 5. Okay, so your b squared minus 4ac here is negative. It's a negative number. So it is a negative number, means cannot factorize. Is it okay? All right. Because if you go and put it to 0, you will get complex roots. So you cannot factorize. Just like what your calculator tell you. Okay, so therefore you cannot do your plan A, your partial fraction. So therefore we go and do plan B. All right, and plan B is called completing square. Is it okay? So let me go and complete square. Let's do one example, complete square. So maybe I type here. Currently is s squared minus 2s plus 5. All right. Yeah, this is the one. This one, let me see how big it is. Yeah, it's correct. Okay, so I want to complete square, right? So meaning of complete square means I want to get s and then plus some constant, then square, okay, and then plus another constant, okay. So now the question is how to get the constant inside there? S plus what square? Do you know how to get the constant inside? Plus, do you know how to get the constant? Yeah, class, do you know or not? The constant is actually b over 2. It's actually b over 2. Right? The constant is b over 2. Constant is b over 2. All right, so that's a constant. So currently our b is -2, the coefficient of s. So if you go and divide by 2, it is -1. Okay, so you know it's s minus 1 square. All right, and plus what? Well, you can put plus 5, doesn't matter. Or the way is the thing is you need to do the balance. All right, your this one actually, what is it? Okay, now this one if you go and multiply out, you know that it's going to be s squared minus 2s and then plus 1. Okay, this square here, s minus 1 square, will give you this. All right, so you compare this with what you have here. The first two terms will match. All right, but the constant doesn't match. So you adjust the constant. All right, currently you got +1, right? But the final one is +5. So that means you are short of 4. So therefore, you know this is 4. It's okay. All right, so that's how it is done. Yep. Okay, so we go and complete square, and then you will get like what I have here. So you get the s minus 1 square plus 4. Still okay? All right. And then after this, still not finished. Now you know that this one is s minus 1. Okay, your denominator here, you've got s minus 1 square. All right. So because of this, your numerator, you also want to make it in terms of s minus 1. Okay. Your denominator got s minus 1, right? So now your numerator, you also want to make it s minus 1, so that later on you can fit certain formula. Okay, yeah. So this is from experience. So you know that your numerator, you also want to put in terms of s minus 1. So now let's go and put here. Currently your numerator is 2s plus 3, right? I hope you can see. I'm typing on the left side now. So your 2s plus 3, you want s minus 1. How to put? So you just put like that. Put s minus 1. Okay, you want s minus 1, right? So you just put s minus 1. But of course, the original one is only s. So you need to plus 1. Okay, so that means you are not changing anything. And then you plus 3. Okay, which is the original one. All right, then after that, then you just multiply out. You treat the s minus 1 as one item. S minus 1, okay, and then plus 2 times 1. 2 times 1 is 2. And then this one is plus 3. Is it okay? So you are treating your s minus 1 here like one single item. That's how you get here. Is that all right or not? Then of course here now becomes 2s minus 1 plus 5. All right. So which is what I have here. So you see I have here 2s minus 1 and then plus 5. Can you all see? All right. I hope you can see. So after this, then you're now ready to inverse Laplace transform. So you inverse Laplace transform. What you do here is you take let me go to highlighter. What do you do is you take this one over denominator and then plus this number over denominator. All right, so that's what you have here. And of course, I think you also realize that my denominator, initially I got a 4, right? But now I go and put 2 square. I think you also see this, right? Why I put 2 square? Well, because if you read Laplace table every night, you know that the form here should be a constant square. All right, so let's go to the Laplace table. Hey, Laplace table is here. Okay, what do you think? The first term, let's talk about the first term first. This first term, which formula fit? Which formula fit? This is the inverse Laplace transform. So you should look at those functions of s. All right, this formula, this expression, which one fits?
10.
Okay. 10, is it? Tan is called tan cosine. So you find that tan fits. All right, tan is this one. Okay, this is tan. All right, can you see it fits? What's your A? A is what? Tell me, what's A?
-1.
Then your omega, ne?
2.
Yeah. So if you can see this, then you can write down this one, right? Of course, with a UT behind. So this is a tan cosine. So that one is okay. That one is tan cosine. Then the second one, the second term, what about the second term? Now I'm talking the second inverse Laplace transform. This one, which one can we fit? 5 over s minus 1 square plus 2 square. Which one? Fit which one? Which one is the closest? The 5 here, because it's a constant, it can be easily adjusted. All right. So if you see this, you just see the denominator, s minus 1 square plus constant square, right? And then your numerator is a constant. All right. So this can fit. I'm not saying that now it fits, but it can fit this one. Okay, it can fit this one. If you want to fit this one, then you know it's tan sine. But to fit this one, your omega is 2. Okay, so you actually need a 2 in the numerator. You need a 2. Currently it is 5, currently not 2. All right, so what you do here is you need a 2, right? So you just put a 2 here. And then, of course, outside, you put a 2, you must divide by 2. So you can put 2 times 5 over 2. Okay, then that will fit very well. Then your 5 over 2, you can bring outside. Okay, so then it becomes like this. Then you see, my 5 over 2 outside. Okay, so this is the tan sine. Yeah, so that will give us the tan sine. Okay, so it will give me like this. And the last step is just simplification. All right, any questions? It's all right, Okay, so finally we come to this question here. Yeah. Well, this one is not a rational function, so we no need to see this partial fraction. So maybe we go and look at time shift, frequency shift, this kind of thing. Okay, so inverse Laplace transform this. Inverse Laplace transform this. So you realize that this function is e to power something, and then your s over s squared plus 16 there is like a function of s, right? So which one is it? Which one is it? Is it this one, or is it this one? Which one? Is it e to power minus st naught times fs? Or is it function of s plus the constant? Which one looks more like it? You need to match, So can you tell me which one more like it? Time shift? Frequency shift? Yeah, class, anyone?
Time shift.
Yeah, actually it's time shift. All right, so you see your e to power minus 2s, right? It's like your e to power minus st naught. Then your fs there will be the remaining function. Okay, so from here you can see that your t naught is what? And your fs is s over s squared plus 16. Is it okay? All right, your t naught is what?
2.
Yeah, so it's like that. Okay, so once you can see this, then you can write down your answer. So your answer will be what? Your answer actually is ft minus t naught, ut minus t naught. So actually I can write like that. FT, I actually can write like this, okay? FTUT, and then outside there, outside, I should like in a subscript like that, okay? How should I express it? Or maybe I change to a smaller font. Oh, cannot. Because I change, everything will change. Okay, so outside there is and actually it's a subscript. So subscript, okay, subscript is how we write subscript. So T equal to T minus T naught. Yep. T minus T naught. T equal to T minus T naught. So actually this means Ft minus T naught, Ut minus T naught. Right? So we know this is the answer. And how to get this answer there? This is a small f, right? So you know the big F, right? From big F, how to get the small f? Okay, from big F, how to get the small f? Oh, it's like this. Your big F inverse Laplace transform give you the small f. Okay, so are we able to inverse Laplace transform this? This one looks familiarly. Yeah, so if you go and look at our table, do you have s over s squared plus 16? We have s over s squared plus 16. It looks like this one, right? S over s squared plus 16. 16 means 4 square. So what is it? It's cosine 4t. Is it okay? It's for cosine 4t ut. All right, so we actually know this already. This is cosine 4t ut. Right? So let's go and write down. So this is our time shift. Okay, so that's what we have. This is inverse Laplace transform capital Fs. So meaning that is your FTUT. All right, and then t equal to t minus 2. Okay, so the inverse Laplace transform of this, actually we already see from here, cosine 4t ut, right? So now you just put your t as t minus 2. So that will give you this. Is that okay? All right, class. Any questions?
Professor, can you shift back to the question 3, part C, please? I have some questions regarding the question.
You mean this one?
Yeah. What on the second line? Like, what's the process over there?
You mean this pink line?
Oh no. Two more lines. Two more lines over there.
You mean here?
Yeah. That line. What's that over there?
Your e to the power minus t sine t minus 2 ut minus 2 is equal to this thing, right?
Yeah, I got that part, but I don't get it. How can you able to separate the e to the power negative 2 outside of the transform?
You mean pull it outside of the Laplace transform?
Yeah. How come it's outside over there?
You mean why I can pull outside?
Yeah.
Oh, okay. Because if you have a constant, it's actually from the definition.
You can put a constant outside.
So
Oh,
in your
all right.
FT here, you've got a constant you can pull outside, right?
Yeah. I got it.
So you can bring outside.
All right. Thank you.
Okay. So the rest, all right, all? Okay. Yep. Okay. So we'll stop here. All right. And we'll meet next week. Okay. Good night, everybody.